Hello everybody. This lesson involves section 7.5 on page 147 of Statistics and Mechanics Book 2 on dynamics and inclined planes. This involves particles moving down a rough plane. Now in chapter 5 we looked at particles moving down a smooth plane. The only difference here is that it has so we have a rough plane, so we have a force of friction involved. And if you remember, when a particle is moving on a rough surface, then the friction force is at its maximum, and F equals mu r. Okay, so what I'll do is I'll go through example 10 then on page 147. So if we just quickly read that. Particle is held at rest on a rough plane which is inclined to the horizontal angle alpha, where tan alpha is 0.75, 3/4. The coefficient of friction between the particle and the plane is 0.5. The particle is released and slides down the plane. Find the acceleration of the particle and the distance it slides in the first 2 seconds. So here is a model of this problem. We have a particle on a slope. The angle tangent at 3/4 is about 36.87. We have mu friction, coefficient of friction 0.5, and if we start, we'll see what happens. The particle slides down the plane, and this indicates we have a constant acceleration. That doesn't change, which means it speeds up. I'll start that again. Moving down the plane. You notice here the reaction, the weight, the friction are not changing as it moves down the plane. The friction 1.96, the reaction 3.92. Friction is half of the reaction. Mu is a half, F equals mu r, and doesn't change. So here we have our particle on a plane, and the plane was about alpha, tan alpha. So that angle is alpha, where tan alpha is 0.75 or 3/4. And now we put on the forces. We have the weight down. Now it didn't tell us the weight, so let's call that mg. M is the mass. We have the reaction R and the friction F, which acts up the plane because it's opposing motion. Remember, it's a particle, so all the forces pass through the same point. Okay, and the first thing we want to find is the acceleration of the particle, so we'll call that A. And what we do is we use Newton's law. We're resolving along the plane and perpendicular to the plane, so parallel to the plane and perpendicular to the plane. Let's go for parallel to the plane first of all, and I'd indicate that as an arrow going that way, vaguely parallel to the plane in that direction, in the direction of the acceleration, in the direction of motion, I should say, in the direction of motion. It's going to move down the plane. So what do we have down the plane? Well, we have F goes up the plane and it's parallel, so that's minus F. R is perpendicular, so there's no components of R, and then we have the component of the weight. Now remember, we need to resolve that. The weight is vertically down, and so we need to resolve it into two components, one which is parallel that way, and then one which is perpendicular that way. So there would be the perpendicular, that would be the parallel, that would be the perpendicular, and the angle, well, the angle is alpha, is between, well, the angle between the parallel and the horizontal is alpha, so the angle between the vertical and the perpendicular is also alpha. So this is mg down. So in this right angle triangle, mg is the hypotenuse. You have mg cos alpha perpendicular and mg sine alpha parallel. Now, always when we have an angle given as a ratio, a trig ratio, you do not need to find the value of the actual angle. If tan alpha is 3/4, so that's like saying this is 3 here and this is 4 here, then the hypotenuse would be 5. And so we have cos alpha is 4/5 and sine alpha is 3/5. So cos alpha 4/5 and sine alpha 3/5. And so we now know what the components are. Mg sine alpha down the plane would be 3/5 mg. So we'd write plus 3/5 mg. And that is equal to, that's all the forces in that parallel to the plane, and that equals mass times acceleration, so ma. And then we're going to resolve perpendicular, so up the plane we have r minus, and then it will be the component of the weight perpendicular to the plane, mg cos alpha, which is 4/5 mg. So that's a 5 there. And that equals 0. So r equals, so from that r equals 4/5 mg. And we know we have limiting friction because it's moving. So we have F equals mu r, and mu is 1/2. So F equals 1/2 of 4/5 mg, 2/5 mg. So then we can substitute that into the first equation. We'll call that equation 1. And that 2. So we have minus 2/5 mg. So 1 in 2. 1 in, where should we say? So 2, I mean, this would be 2 in 1 really, wouldn't it? 2 in 1. Minus 2/5 mg plus 3/5 mg equals ma. And you notice there the m's cancel. We've got ma is 3/5 minus 2/5 is a 5th mg, so a is a 5th g. I might just mention that in my model here, if you see that moving down the plane, I've set m as 1/2. If I were to change m, make it much bigger, like that. Remember, the forces are bigger, but the acceleration and the velocity, if you see, doesn't change. If you see what that looked like, reset. I'll make the mass very small. And you can see there when it sets up the acceleration here, it's got the same length, so it's got the same value, and it moves down in the same with the same speed. In other words, acceleration is independent of mass, and you can see that in the equation because the mass is cancels, and it's not, acceleration is not dependent on the mass, which is why we don't need to have the mass in the question. Okay, so that was the first part, is to find the acceleration. The next part is to find the distance the particle travels in 2 seconds. So it's going to move in 2 seconds from there to there. This is 2 seconds. How far does it go? Well, now we look and we notice that acceleration is constant. So part B involves using the equations for constant acceleration. So that we want to know how the displacement after 2 seconds, it started from rest, so that's 0. The acceleration is a fifth g, and it's in 2 seconds. And so we don't have v, and if we don't have v, the equation to use is s equals ut plus a half at squared. So s is equal to 0 times t plus a half times a fifth g times 2 squared, which is 4. So that is going to be 2/5 g. And 2/5 g is approximately, well, it's about 3.92, or approximately 3.9 meters. And so the particle moves 3.9 meters in 2 seconds. Okay.